Alright everybody, this is just a little video to serve as test review for the centripetal motion and gravitation unit, chapter 6. I've got a test sitting right next to me, so I'm going to use that to sort of guide what happens here to sort of give you the best possible review for the test. So it'll be sort of, choppy a little bit as I sort of search through for particular questions, but I'm going to pretty much work straight on through the test, giving some sample problems and highlighting some of the concepts that you need to know. So first thing I want to discuss is the direction of different sort of ideas or numbers or values when it comes to uniform circular motion. So first off, we have a couple different ones. So I'm going to say that we're starting from a point over here on the right side of this circle, and there are three sort of concepts that we had. We had acceleration, which was v squared over r, and net force, which was mv squared over r. So I guess really just two here. So the acceleration is always into the center of our circle. From whatever point we're at, if we're over here, then our acceleration would point there. It's always toward the center. And the same is true for that net force. Net force is also always towards the center. That's sigma F. They are both always toward the center. In order for us to keep moving in a circle, the net force has to be consistently towards the center. On this diagram also, let's say that we are moving, let's do clockwise. So at this point here, our velocity is going to be a tangent to the circle, and in this case it's going to be pointing downward. So if we sort of followed that path of the motion, we said it was going clockwise, and when we get to this spot, we keep moving straight down that way. Over here, we would point there, and here we would point up and over there. If we were to flip-flop and be moving counterclockwise, each one of these would reverse. So over here, it would be then moving up if it was counterclockwise. Down here, it would be moving to the right, and over here, we would be moving sort of down and to the left. So these two equations are sort of our big ones for the entire unit. We've got our acceleration and our net force. We can treat these very similarly to the way we did net force equals ma in the last unit, but it's a little bit more, it's a little bit different. Instead of accelerating by changing the speed, we are just changing the direction. Uniform circular motion is still accelerated motion. It is constantly being accelerated toward that center. So let's do a sample problem. Let's say that we want to calculate the centripetal acceleration of an object that has a mass of 35 kilograms. And let's say it's moving in a circular path that has a radius of 15 meters. And it's going at a velocity of 12 meters per second. So I want to find my acceleration centripetally, my centripetal acceleration. Just a little note, acceleration is not a force. I've heard a couple people when we're trying to identify forces acting on various objects. Acceleration is not a force. If a question asks you what force is acting, you should be thinking normal force, gravity, the force of friction, maybe tension. Acceleration is not a force. Acceleration is caused by forces. At the same time, centripetal force is not a type of force. It is a classification. Any type of force can act centripetally. A centripetal force is not specific at all. It's very general. So if a question asks you what type of force, or you're drawing a free body diagram, there is no centripetal force there. We're talking gravity, normal force, tension. So our equation, back to this problem, our equation for the acceleration is v squared over r. So I just plug in my acceleration is equal to 12 squared over 15. Simplifying that a little bit, we get 144 over 15. So it is a little bit less than 100, or I'm sorry, a little bit less than 10. It's going to be 9. Let's see, 9.66, and that is meters per second squared. Let me double check that on a calculator. 44 over 15, yeah, 9 point, oh, it says 0.6, not 0.66. Where's that? So yeah, 9.6 meters per second squared. It's still meters per second squared, just like our accelerations have been in the past. So moving sort of one step further, we can then find the net force. We can find the force that's acting centripetally, the total force, and that is mv squared over r. So we already did the v squared over r part. That's just our acceleration. So we can substitute that in. We've got the net force equals the mass of 35 kilograms times v squared over r, which we found to be 9.6. So our net force is going to be equal to 336 newtons. The only way that this can be made a little bit more challenging is if instead of giving you a velocity, let's see if I can move that up a little bit further, you're just given a radius and a period, the time it takes to go around the circle. So a couple things, more equations to remember. The circumference of a circle is 2 pi r, and velocity for these circles is 2 pi r over t. That t is the period, the time it takes to go around a loop one time. So let's say that for this problem up above, instead of giving you the velocity, I still had that radius of 15. So let's say I said it was still a 15 meter radius. But this time, instead of just giving you the velocity, I said, well, it takes 6.7 seconds to go around the circle one time. That is our period. And by working with the circumference, we can then find the velocity. The velocity is just the circumference over the time it takes to go around the circle. It's still distance over time, but we have to be a little bit more specific. So first, I'm going to find the distance around that circle, and that is 2 pi times the radius, which was 15. So 30 pi, or 94.2 meters is my circumference. So my velocity is going to be 94.2 over this 6.7 seconds. So 94.2 divided by 6.7, and I'm left with a velocity of 14.1 meters per second. And from here I could take that velocity and put it back into, mv squared over r, or just v squared over r, and then I can use this velocity as if it had just been given to me in the problem. And lastly, occasionally a problem will give you just the mass and acceleration. It'll give you, the mass is 12 kilograms. The acceleration is 3.7 meters per second squared. That's done all the work for you. Net force is still just ma. So if that's the case, if you have a mass and you have an acceleration, you can find the net force. You don't have to do any v squareds over r's or any of that stuff. Net force still does equal ma. Next type of problem I want to take a look at are the ones we did today in class, both the loops and the flat turns. So first off, the flat turn. Remember that as a car turns around a corner, it is the force of friction that holds it inside that turn. That is not the normal force or the weight. Force of friction against the tires, it is static friction. And with that, today during class I did show you guys how we got here, but the real takeaway is that the velocity is equal to the square root of mu sub s, that is mu, times the gravitational acceleration, which is 10, times the radius, which is whatever it is. This is the max speed around a turn. if you go any faster than this, you will not be moving in uniform circular motion. You'll be going too fast, you will slip, which will result in you actually breaking that circular motion. You can do it, it's physically possible, but if you go faster, you will not be moving in that circle anymore. So let's say that we had a mu sub s of, let's call it 0.8, some decent tires. And let's say that we had a radius around that the person's trying to go of 30 meters. And we wanted to know the maximum velocity. So we would just substitute in. Mu sub s is 0.8 is mu sub s, but our velocity is the square root of that mu sub s times the acceleration due to gravity, which is 10, times that radius, which is 30. So 300 times 0.8, and then we take the square root of that, 240, and we end up with 15.5 meters per second there. The last type of problem we had was a car going around a loop-the-loop or a roller coaster or whatever going, and we wanted to know what the minimum speed at the top was. Minimum speed at top. We can go really as fast as we want, but we have to at least be going fast enough so that the weight, the mg pulling downward here, mg, is equal to the mv squared over r. There is also a normal force here, but to be going at our slowest speed, we want that normal force to be as close to zero as possible. And again, during class, I showed you sort of how to work this out to get the square root of gr equals v. That is the minimum speed at the top. If we want to complete this loop, we have to be going at least that speed. So a problem could give you a couple of these variables and ask you to solve for the other one. Notice that mass, and this is true for the previous one, mass does not matter. It does not matter how much mass your car has as it's trying to go around these flat turns or go through these loop-the-loops. It has absolutely no effect on how fast the object has to be going. There might have to be more force put in to get that object moving at that speed, but as far as the actual speed it has to be going, mass does not matter. All right, when we come and get to talking about variables, I am going to come back to that centripetal motion a little bit at the very end, but I do want to get into gravity. Our big equation here is that the force of gravity is equal to capital G, the universal gravitational constant, times the mass of the first object, mass of the second object, over r squared. Remember this square there. The biggest mistake that I imagine will happen for a lot of people is forgetting about that squared, and you're in for a bad time if that is the case. So a couple sort of conceptual things about this. If we increase either of the masses, so if masses increase, so does the force of gravity. If the masses increase, the force of gravity increases. If we've got more massive objects, they're going to have a stronger gravitational pull. That being said, if we increase the distance, which is that r on the bottom, if we increase it, the force decreases. They are inversely proportional, or sort of proportional to the square of that distance. So if one goes up, the other goes down. So the only way that we can sort of lessen the pull of gravity is either by decreasing the masses or increasing the distance. And we'll get to some variables with that here in a second. But sort of the idea here is just being able to plug in values. Remember that G is 6.67 times 10 to the negative 11th. That will be given to you. But otherwise, it's just plugging in numbers. Plug in the mass of the first one, plug in the mass of the second one, divide it by the distance between the two centers squared. And that's going to be the biggest issue for people, I would imagine. Whenever we have two objects that are exerting a gravitational force on each other, so let's call this planet 1 and call this one planet 2. The force that planet 2 applies to planet 1, so that's this force right here. It is the force of planet 2 on planet 1, and then we also have the force that planet 1 applies on planet 2. These two forces are equal. Newton's third law says that any action has an equal and opposite reaction. So if one is giving a gravitational force, the other is also being, is also pulling on the first one. So they are equal in magnitude, opposite in direction. But if we were to compare the gravitational force that one planet exerts on the other, the force, if we flip-flop that, would be the exact same. There's not a second equation, so you would plug in both of those masses again and you would get the exact same number there. If, let's say that the Earth suddenly expanded out in all directions. So in all directions the Earth expanded and got bigger, but its mass stayed the same. And we were on the planet when all of this happened. So there's our little guy. If that were to happen, if we were to expand out, the mass of the planet has stayed the same, but the distance to the center is now larger, which means that the force of gravity here is smaller than it was back here. We are farther away, so it's smaller here than it was here. It's bigger. And last little sort of conceptual thing before we get into those variables is that gravity affects everything. Gravity affects everything. Everything in the universe exerts gravity, and everything that exerts gravity is exerting it on everything else. There is no limit to it. So to answer the sort of question, well, if that's the case, then why doesn't stuff just immediately become attracted to me and stick to me? Why is my gravity, the gravity that my body is exerting, not noticeable in every day? And the reason for it is our mass is much too small. On the small scale, gravity is the weakest of the forces. The only reason that gravity affects the planets and sort of the heavenly bodies is because they are so darn big. Their masses are gigantic to overcome that universal gravitational constant, that's 6.67 times 10 to the negative 11th. That is a massively small number. So gravity affects everything. The reason is that we don't sort of see it, just kind of walking around, is because the gravitational force that you exert, or that sort of everyday objects exerts, is much smaller than other forces. For instance, friction, or the weight that the planet, or I'm sorry, the gravity that the planet that we're sitting on is exerting. So our gravity, the gravity that we are causing, sort of gets washed out by larger forces. All right, last sort of topic for this is going to be changing variables, changing by factors. So for gravity, we have this equation, this sort of side of the equation, m1, m2 over r squared. So let's say that the distance between two objects suddenly quadrupled. So the r quadrupled, the r became times 4. It said it got 4 times bigger. But the mass of one of the objects doubled, and the mass of the second object became a third of what it was. So these three things happen. A test question might only ask you about one, might ask you about two, just sort of keep them straight. So here we've got the radius is 4 times as big as it was. So we're going to say that this 4 is on the bottom. It is still being squared. we do not just ignore that squared. It has to be there here as well. This big G here did not change at all. It is still the same. So we could say that it got multiplied by 1. And the mass 1, it said, doubled. And mass 2 was multiplied by a third. It is a third as big as it was. So what we're left with is 2/3 over 16, which ends up being 2 over 48, or 1 over 24. That means that whatever gravitational force was before is now a 24th of what it was. It has decreased by a 1/24. It is a 24th times as great. What are there? It is a 24th times what it was. So it is not now a 1/24 of a Newton. It is just 1/24 times what it was. Biggest thing here to remember is that squared right there. That I imagine is going to be the biggest issue. So let's say, for example, we'll actually do some of this. Let's say that two objects had a force of gravity between them of 40 newtons. That was their original force between them. But the mass of one of the objects, suddenly doubled. And the distance was cut in half. I want to know what the new force of gravity is. What is the new force of gravity? So I started with 40 newtons. I'm going to sort of put that to the side for a second. And back from that equation, my capital G did not change. It still stayed the same. It's a 1. It's always going to be a 1. Our universal gravitational constant does not change. So then one of my masses, it said doubled. The mass of one of the objects doubled, so that is 2 times. The mass of my second object did nothing, so it is a 1 as well. And the distance is now a half. That 1/2 gets squared. So then I've got 2 over a fourth. When you divide by a fraction, you have to multiply by the reciprocal. So I'm left with 2 times 4, which is 8. 8 is not my final answer. That is sort of my multiplier. It is 8 times bigger. So originally it was 40 newtons from up above, times 8. And that gives me 320 newtons. That is my new force of gravity between those two objects. It is not 8. We have to multiply it by the original to get our new. We can work with these variables actually in the exact same way with either centripetal force or centripetal acceleration. We have these two equations. We've either got mv squared over r, which equals the net force, or we've got the acceleration, which is just v squared over r. So let's say that, let's see what we got here on this test. I can switch them up a little bit. So let's say that a car travels around a curve once, and it has an acceleration of a. So that's its original acceleration. But then it travels again on a new curve where the velocity has been tripled. He's going 3 times as fast. So my velocity is 3 times, but my radius is a quarter of what it was. So I want to know what my new acceleration would be in terms of the original acceleration of A. So let's just go and plug these in just like we did in the previous one. We're just plugging these into sort of that equation. It's 3 times bigger, and that 3 gets squared, so it is 9 over a fourth of the radius. So 9 divided by a fourth is the same as 9 times 4, which is 36. This means that my acceleration is 36 times bigger than it was. If it was a before, it is now 36a. And again, we can do the same thing if the car's mass changed. Let's say that the mass was also a third of what it was. So I could do, and using the same variables from over here, and I wanted to know what the change in the net force was, I could say 1/3 here, and that is still times 3 squared over a quarter, which leaves us with 3 over a quarter, which is just 12 this time. So that is 12 times the original net force. The net force is 12 times bigger than what it was. If it was F, then it would now be 12F. If it was 10, it would now be 120. We just multiply those two things together, whatever that original is. But just leaving this as it is might not get you the answer that you need. Thankfully, these are multiple choice, so you should be helped by that. And that's about it. That's about all that is on the test. Tomorrow we'll practice some more during class. But if you are good with these working with variables and you can remember those equations from centripetal motion, again, I'll just write them out right here. Remember, these are all the equations that we need. The circumference is 2 pi r, and the velocity is 2 pi r over t, and that is the period. Acceleration is v squared over r, and net force equals mv squared over r. Couple particular cases, we've got v equals the square root of mu sub s gr, and we've got v equals the square root of just gr. This is the max speed around a turn. And on the bottom here, we've got the minimum speed at the top of a loop. Those equations are really for centripetal motion and are only one for gravity. The force of gravity is capital G, m1, m2 over r squared. Remember that squared is here with Fg. It is not here with net force. Our r squared is part of gravity. So keep that in mind. Hopefully this helps everybody who decides to give it a listen. And I will see you all tomorrow.